II, non-parametric or distribution-free tests. It has already been stated in earlier chapters that a statistical test is a formal technique, based on some probability distribution, for arriving at a decision about the reasonableness of an assertion or hypothesis. The test technique makes use of one or more values obtained from sample data, often called test statistics, to arrive at a probability statement about the hypothesis. But such a test technique also makes use of some more assertions about the population from which the sample is drawn. For instance, it may assume that population is normally distributed, sample drawn is a random sample, and similar other assumptions. The normality of the population distribution forms the basis for making statistical inferences about the sample drawn from the population. But no such assumptions are made in case of non-parametric tests.
In a statistical test, two kinds of assertions are involved, viz. An assertion directly related to the purpose of investigation and other assertions to make a probability statement. The former is an assertion to be tested and is technically called a hypothesis, whereas the set of all other assertions is called the model. When we apply a test to test the hypothesis without a model, it is known as distribution-free test, or the non-parametric test. Non-parametric tests do not make an assumption about the parameters of the population and thus do not make use of the parameters of the distribution. In other words, under non-parametric or distribution-free tests we do not assume that a particular distribution is applicable, or that a certain value is attached to a parameter of the population. For instance, while testing the two training methods, say A and B, for determining the superiority of one over the other, if we do not assume that the scores of the trainees are normally distributed or that the mean score of all trainees taking method A would be a certain value, then the testing method is known as a distribution-free or non-parametric method. In fact, there is a growing use of such tests in situations when the normality assumption is open to doubt. As a result, many distribution-free tests have been developed that do not depend on the shape of the distribution or deal with the parameters of the underlying population. The present chapter discusses few such tests. 284 Research methodology. Important non-parametric OR distribution-free tests. Tests of hypotheses with order statistics, or non-parametric statistics, or distribution-free statistics are known as non-parametric or distribution-free tests. The following distribution-free tests are important and generally used. I test of a hypothesis concerning some single value for the given data, such as one sample sign test. E test of a hypothesis concerning no difference among two or more sets of data, such as two sample sign test, Fisher-Irwin test, rank sum test, etc. E test of a hypothesis of a relationship between variables, such as rank correlation, Kendall's coefficient of concordance, and other tests for dependence. IV test of a hypothesis concerning variation in the given data, i.e., test analogous to ANOVA, viz. Kruskal-Wallis test. V tests of randomness of a sample based on the theory of runs, viz. One sample runs test. V test of hypothesis to determine if categorical data shows dependency or if two classifications are independent, viz. the chi-square test. The chi-square test has already been dealt with in Chapter 10. The chi-square test can as well be used to make comparison between theoretical populations and actual data when categories are used. Let us explain and illustrate some of the above stated tests which are often used in practice. 1. Sign tests. The sign test is one of the easiest parametric tests. Its name comes from the fact that it is based on the direction of the plus or minus signs of observations in a sample and not on their numerical magnitudes. The sign test may be one of the following two types: A. One sample sign test, B. Two sample sign test. A. One sample sign test. The one sample sign test is a very simple non-parametric test applicable when we sample a continuous symmetrical population, in which case the probability of getting a sample value less than mean is 1/2 and the probability of getting a sample value greater than mean is also 1/2. To test the null hypothesis, micro equals h0 against an appropriate alternative on the basis of a random sample of size, n, we replace the value of each and every item of the sample with a plus sign if it is greater than micro h0, and with a minus sign if it is less than micro h0. But if the value happens to be equal to micro h0, then we simply discard it. After doing this, we test the null hypothesis that these plus n signs are values of a random variable, having a binomial distribution with p equals 1/2. For performing one sample sign test when the sample is small, we can use tables of binomial probabilities, but when sample happens to be large, we use normal approximation to binomial distribution. Let us take an illustration to apply one sample sign test. If it is not possible for one reason or another to assume a symmetrical population, even then we can use the one sample sign test, but we shall then be testing the null hypothesis micro equals H0, where micro is the population median. Testing of hypotheses 285 Illustration 1 Suppose playing 4 rounds of golf at the City Club 11 professionals totaled 280, 282, 290, 273, 283, 283, 275, 284, 282, 279, and 281. Use the sign test at 5% level of significance to test the null hypothesis that professional golfers average micro H0 equals 284 for 4 rounds against the alternative hypothesis micro H0 less than 284. Solution. To test the null hypothesis micro H0 equals 284 against the alternative hypothesis micro H0 less than 284 at 5%, or 0.05 level of significance, we first replace each value greater than 284 with a plus sign and each value less than 284 with a minus sign and discard the one value which actually equals 284. If we do this we get plus. Now we can examine whether the 1 plus sign observed in 10 trials support the null hypothesis p equals 1/2 or the alternative hypothesis p less than 1/2. The probability of 1 or fewer successes with n equals 10 and p equals 1/2 can be worked out as under 10119 1000 10190 1010 12 112 CPQ plus equals FHGIKJ plus FHGIKJ equals 0.010 plus 0.001. These values can also be seen from the table of binomial probabilities when p equals 1/2 and n equals 10 equals 0.011. Since this value is less than alpha equals 0.05, the null hypothesis must be rejected. In other words, we conclude that professional golfers' average is less than 284 for 4 rounds of golf. Alternatively, we can as well use normal approximation to the binomial distribution. If we do that, we find the observed proportion of success, on the basis of signs that we obtain, is 1/10 and that of failure is 9/10. The standard error of proportion assuming null hypothesis p equals 1/2 is as under, sigma prop equals dot operator equals times equals pqn 121210015881. For testing the null hypothesis i.e., p equals 1/2 against the alternative hypothesis p less than 1/2, a one-tailed test is appropriate which can be indicated as shown in the Fig. 12.1. By using table of area under normal curve, we find the appropriate z-value for 0.45 of the area under normal curve and it is 1.64. Using this, we now work out the limit on the lower side as the alternative hypothesis is of less than type of the acceptance region as under pz minus dot operator sigma prop bg or p 1.64 0.1581 or 1202593 minus or 0.2407 asterisk table number 8 given in appendix at the end of the book. 286 Research methodology p 1.64 limit 0.05 of area s prop 0.45 of area 0.2407 p equals 1/2 shaded portion indicates rejection region. Fig. 12.1 is the observed proportion of success is only 1/10 or 0.1 which comes in the rejection region. We reject the null hypothesis at 5% level of significance and accept the alternative hypothesis. Thus, we conclude that professional golfers' average is less than 284 for 4 rounds of golf. B2 Sample sign test, or the sign test for paired data. The sign test has important applications in problems where we deal with paired data. In such problems, each pair of values can be replaced with a plus sign if the first value of the first sample, say x, is greater than the first value of the second sample, say y, and we take minus sign if the first value of x is less than the first value of y. In case the two values are equal, the concerning pair is discarded. In case the two samples are not of equal size, then some of the values of the larger sample left over after the random pairing will have to be discarded. The testing technique remains the same as started in case of one sample sign test. An example can be taken to explain and illustrate the two sample sign test. Illustration 2. The following are the numbers of artifacts dug up by 2 archaeologists at an ancient cliff dwelling on 30 days. By X by Y. 102321212321212121212102202110211021210101010 Use the sign test at 1% level of significance to test the null hypothesis that the two archaeologists, X and Y, are equally good at finding artifacts against the alternative hypothesis that X is better. Solution. First of all, the given paired values are changed into signs plus or as under. Testing of Hypotheses II 287 Table 12.1 by X1023102231114121352132132413202242 by Y001012021212202302101010 sign plus 0 plus 0 plus 0 plus 0 plus X. Y total number of plus signs equals 20 total number of signs equals 6 hence, sample size equals 26 since there are 4 zeros in the sign row and as such 4 pairs are discarded, we are left with 30 to 4 equals 26. Thus the observed proportion of pluses or successes in the sample is equals 20/26 equals 0.7692 and the observed proportion of minuses or failures in the sample is equals 6/26 equals 0.2308. As we are to test the null hypothesis that the two archaeologists X and Y are equally good, and if that is so, the number of pluses and minuses should be equal and as such P equals 1/2 and Q equals 1/2. Hence, the standard error of proportion of successes, given the null hypothesis and the size of the sample, we have sigma prop equals dot operator equals times equals PQN121226000981. Since the alternative hypothesis is that the archaeologist's X is better, or P greater than 1/2, we find one-tailed test is appropriate. This can be indicated as under, applying normal approximation to binomial distribution in the given case, Fig. 12.20.01 of area 0.49 of area limit 0.7276 P equals 1/2 P plus 2.32 S prop shaded area represents rejection region. 288 Research methodology. By using the table of area under normal curve, we find the appropriate z-value for 0.49 of the area under normal curve and it is 2.32. Using this, we now work out the limit on the upper side as the alternative hypothesis is of greater than type of the acceptance region as under 232 P plus equals plus op sigma PR 0.5232000981 BG equals 0.5 plus 0.2276 equals 0.7276 and we now find the observed proportion of successes as 0.7692 and this comes in the rejection region and as such we reject the null hypothesis at 1% level of significance that two archaeologists X and Y are equally good. In other words, we accept the alternative hypothesis and thus conclude that archaeologist X is better. Sign tests, as explained above, are quite simple and they can be applied in the context of both one-tailed and two-tailed tests. They are generally based on binomial distribution, but when the sample size happens to be large enough such that NP.operator and NQ.operator both happen to be greater than 5, we can as well make use of normal approximation to binomial distribution. 2. Fisher-Irwin test. Fisher-Irwin test is a distribution-free test used in testing a hypothesis concerning no difference among two sets of data. It is employed to determine whether one can reasonably assume, for example, that two supposedly different treatments are in fact different in terms of the results they produce. Suppose the management of a business unit has designed a new training program which is now ready and as such it wishes to test its performance against that of the old training program. For this purpose a test is performed as follows. 12 newly selected workers are chosen for an experiment through a standard selection procedure so that we presume that they are of equal ability prior to the experiment. This group of 12 is then divided into two groups of 6 each, one group for each training program. Workers are randomly assigned to the two groups. After the training is completed, all workers are given the same examination and the result is as under. Table 12.2 No passed new training A, 5 old training B, 3 no failed total 1636 total 8412. A casual look of the above result shows that the new training program is superior. But the question arises, is it really so? It is just possible that the difference in the result of the two groups may be due to chance factor. Such a result may occur even though the two training programs were equally good. Then how can a decision be made? We may test the hypothesis for the purpose. The hypothesis is that the two programs are equally good. Prior to testing, the significance level or the alpha value must be specified, and supposing the management fixes 5% level for the purpose, which must invariably be respected following the test to guard against bias entering into the result and to avoid the possibility of vacillation on the part of the decision maker. The required probability that the particular result or a better one for a group would occur if the two training programs were, in testing of hypotheses 289 fact, equally good. Alternatively, the probability that the particular result or worse for B group would occur be worked out. This should be done keeping in view the probability principles. For the given case, the probability that Group A has the particular result or a better one, given the null hypothesis that the two programs are equally good, is as follows: PR of Group A doing as well or better equals PR 5 passing and 1 failing plus PR 6 passing and 0 failing equals times 8 5 4 1 1 2 6 8 6 4 0 1 2 6 C equals 2 2 4 9 2 4 2 8 9 2 4 0 2 4 0 3 0 2 7. Alternatively, we can work out as under: PR of Group B doing as well or worse equals PR 3 passing and 3 failing plus PR 2 passing and 4 failing equals times 8 3 4 3 1 2 6 8 2 4 4 1 2 6 C equals 2 2 4 9 2 4 2 8 9 2 4 0 2 4 0 3 0 2 7. Now we have to compare this calculated probability with the significance level of 5% or 0.05 already specified by the management. If we do so, we notice that the calculated value is greater than 0.05 and hence, we must accept the null hypothesis. This means that at a significance level of 5% the result obtained in the above table is not significant. Hence, we can infer that both training programs are equally good. This test, Fisher-Irwin test illustrated above, is applicable for those situations where the observed result for each item in the sample can be classified into one of the two mutually exclusive categories. For instance, in the given example the worker's performance was classified as fail or pass, and accordingly numbers failed and passed in each group were obtained. But supposing the score of each worker is also given and we only apply the Fisher-Irwin test as above, then certainly we are discarding the useful information concerning how well a worker scored. This in fact is the limitation of the Fisher-Irwin test, which can be removed if we apply some other test, say, Wilcoxon test as stated in the pages that follow. 3. McNemar test. McNemar test is one of the important nonparametric tests often used when the data happen to be nominal and relate to two related samples. As such, this test is specially useful with before-after measurement of the same subjects. The experiment is designed for the use of this test in such a way that the subjects initially are divided into equal groups as to their favorable and unfavorable views about, say, any system. After some treatment, the same number of subjects are asked to express their views about the given system, whether they favor it or do not favor it. Through McNemar test we in fact try to judge the significance of any observed change in views of the same subjects before 290 research methodology and after the treatment by setting up a table in the following form in respect of the first and second set of responses. Table 12.3 before treatment, after treatment, do not favor A, B do not favor C, D. Since A plus D indicates change in people's responses, B plus C shows no change in responses. The expectation under null hypothesis H0 is that A plus D two cases change in one direction and the same proportion in other direction. The test statistic under McNemar test is worked out as under, as it uses the under-mentioned transformation of chi-square test, chi221 equals minus plus ADADCHBG with D, F equals 1. The minus 1 in the above equation is a correction for continuity, as the chi-square test happens to be a continuous distribution, whereas the observed data represent a discrete distribution. We illustrate this test by an example given below. Illustration 3. In a certain before-after experiment, the responses obtained from 1,000 respondents, when classified, gave the following information: before treatment, after treatment, unfavorable, favorable response, favorable response 200 equals A, 300 equals B, unfavorable response 400 equals C, 100 equals D. Test at 5% level of significance, whether there has been a significant change in people's attitude before and after the concerning experiment. Solution. In the given question we have nominal data and the study involves before-after measurements of the two related samples. We can use appropriately the McNemar test. We take the null hypothesis H0 that there has been no change in people's attitude before and after the experiment. This, in other words, means that the probability of favorable response before and unfavorable response after is equal to the probability of unfavorable response before and favorable response after, i.e., H0 PA equals PD. We can test this hypothesis against the alternative hypothesis, viz. PA does not equal PD. Testing of Hypotheses II 291. The test statistic, utilizing the McNemer test, can be worked out as under chi2 2 2 1 200 100 1 200 100 equals minus minus plus equals minus minus plus ADAD CHBG equals times equals 9999 300 3267. Degree of freedom equals 1. From the chi-square distribution table, the value of chi2 for 1 degree of freedom at 5% level of significance is 3.84. The calculated value of chi2 is 32.67, which is greater than the table value, indicating that we should reject the null hypothesis. As such, we conclude that the change in people's attitude before and after the experiment is significant. 4. Wilcoxon matched pairs test or signed rank test in various research situations in the context of two related samples, i.e., case of matched pairs such as a study where husband and wife are matched, or when we compare the output of two similar machines, or where some subjects are studied in context of before-after experiment. When we can determine both direction and magnitude of difference between matched values, we can use an important non-parametric test, viz. Wilcoxon matched pairs test. While applying this test, we first find the differences d between each pair of values and assign rank to the differences from the smallest to the largest without regard to sign. The actual signs of each difference are then put to corresponding ranks and the test statistic t is calculated, which happens to be the smaller of the two sums, viz. the sum of the negative ranks and the sum of the positive ranks. While using this test, we may come across two types of tie situations. One situation arises when the two values of some matched pairs are equal, i.e., the difference between values is 0, in which case we drop out the pairs from our calculations. The other situation arises when two or more pairs have the same difference value, in which case we assign ranks to such pairs by averaging their rank positions. For instance, if two pairs have rank score of 5, we assign the rank of 5.5, i.e., 5 plus 6 2 equals 5.5 to each pair, and rank the next largest difference as 7. When the given number of matched pairs after considering the number of dropped-out pairs, if any, as stated above is equal to or less than 25, we use the table of critical values of T, table number 7 given in appendix at the end of the book, for the purpose of accepting or rejecting the null hypothesis of no difference between the values of the given pairs of observations at a desired level of significance. For this test, the calculated value of T must be equal to or smaller than the table value in order to reject the null hypothesis. In case the number exceeds 25, the sampling distribution of T is taken as approximately normal, with mean UT equals n plus 1 4 and standard deviation sigma T n equals plus 1 2 1 2 4 bg, where n equals number of given matched pairs, number of dropped out pairs, if any, and in such situation the test statistic Z is worked out as under. 292 Research methodology ZTUTT equals minus sigma. We may now explain the use of this test by an example. Illustration 4. An experiment is conducted to judge the effect of brand name on quality perception. 16 subjects are recruited for the purpose and are asked to taste and compare two samples of product on a set of scale items judged to be ordinal. The following data are obtained. Pair brand A, brand B 1 7 3 5 1 2 4 3 4 1 3 4 7 4 3 4 5 3 4 1 5 5 8 4 7 6 4 7 3 2 7 5 2 2 4 8 5 8 5 8 9 3 8 4 3 1 0 6 1 5 3 1 1 5 6 5 2 1 2 5 6 5 7 1 3 3 4 4 4 1 4 5 5 5 7 1 5 6 5 4 0 1 6 7 5 6 8. Test the hypothesis, using Wilcoxon matched pairs test, that there is no difference between the perceived quality of the two samples. Use 5% level of significance. Solution. Let us first write the null and alternative hypotheses as under. H0. There is no difference between the perceived quality of two samples. There is difference between the perceived quality of the two samples. Using Wilcoxon matched pairs test, we work out the value of the test statistic T as under. Table 12.4 Pair brand A, brand B, difference rank of rank with signs D plus 1 7 3 5 1 2 2 1 3 1 3 2 4 3 4 1 2 2.5 2.5, conded. Hollow circle, hollow circle, hollow circle, hollow circle. Testing of Hypotheses II 293 Pair 3 brand A 47 brand B 43 difference DI4 rank of D4 5 4 5 3 4 1 1 2 1 rank with signs plus 4.5 1 11 5 5 8 4 7 1 1 1 0 1 0 6 4 7 3 2 1 5 1 2 1 2 75224281515, 8585809384356, 610-611-1213-1415563552576575455352576575406810-225 84.5192.51477 total hence, 84.5, 14 7101.5 t equals 18.5, 1 to 9 minus 2.5, minus 18.5 we drop out pair 8 is D. Value for this is 0 and as such Rn equals 16 to 1 equals 15 in the given problem. The table value of t at 5% level of significance when n equals 15 is 25 using a two-tailed test because our alternative hypothesis is that there is difference between the perceived quality of the two samples. The calculated value of t is 18.5 which is less than the table value of 25. As such we reject the null hypothesis and conclude that there is difference between the perceived quality of the two samples. 5. Rank sum tests. Rank sum tests are a whole family of tests, but we shall describe only two such tests commonly used viz. The U-test and the H-test. U-test is popularly known as Wilcoxon-Mann-Whitney test, whereas H-test is also known as Kruskal-Wallis test. A brief description of the said two tests is given below. A Wilcoxon-Mann-Whitney test, or U-test. This is a very popular test amongst the rank sum tests. This test is used to determine whether two independent samples have been drawn from the same population. It uses more information than the sign test or the Fisher-Irwin test. This test applies under very general conditions and requires only that the populations sampled are continuous. However, in practice even the violation of this assumption does not affect the results very much. To perform this test, we first of all rank the data jointly, taking them as belonging to a single sample in either an increasing or decreasing order of magnitude. We usually adopt low to high ranking process, which means we assign rank 1 to an item with lowest value, rank 2 to the next higher item and so on. In case there are ties, then we would assign each of the tied observation the mean of the ranks which they jointly occupy. For example, if 6th, 7th and 8th values are identical, we would assign each the rank 6 plus 7 plus 8 3 equals 7. After this we find the sum of the ranks assigned to the 294 research methodology values of the first sample and call it R1, and also the sum of the ranks assigned to the values of the second sample and call it R2. Then we work out the test statistic, i.e., U, which is a measurement of the difference between the ranked observations of the two samples as under UNNNR equals dot operator plus plus minus 1211112 bg, where N1 and N2 are the sample sizes and R1 is the sum of ranks assigned to the values of the first sample. In practice, whichever rank sum can be conveniently obtained can be taken as R1, since it is immaterial which sample is called the first sample. In applying U-test we take the null hypothesis that the two samples come from identical populations. If this hypothesis is true, it seems reasonable to suppose that the means of the ranks assigned to the values of the two samples should be more or less the same. Under the alternative hypothesis, the means of the two populations are not equal, and if this is so, then most of the smaller ranks will go to the values of one sample while most of the higher ranks will go to those of the other sample. If the null hypothesis that the N1 plus N2 observations came from identical populations is true, the said U statistic has a sampling distribution with mean equals micro UNN equals dot operator 122 and standard deviation, or the standard error equals sigma UNNNN equals plus plus 1 2 1 2 1 1 2 bg if N1 and N2 are sufficiently large, i.e., both greater than 8, the sampling distribution of U can be approximated closely with normal distribution and the limits of the acceptance region can be determined in the usual way at a given level of significance. But if either N1 or N2 is so small that the normal curve approximation to the sampling distribution of U cannot be used, then exact tests may be based on special tables such as one given in the appendix, asterisk showing selected values of Wilcoxon's unpaired distribution. We now can take an example to explain the operation of U-test. Illustration 5. The values in one sample are 53, 38, 69, 57, 46, 39, 73, 48, 73, 74, 60 and 78. In another sample they are 44, 40, 61, 52, 32, 44, 70, 41, 67, 72, 53 and 72. Test at the 10% level the hypothesis that they come from populations with the same mean. Apply U-test. Solution. First of all, we assign ranks to all observations, adopting low to high ranking process on the presumption that all given items belong to a single sample. By doing so we get the following. Table number 6 given in appendix at the end of the book. Testing of Hypotheses II 295 Table 12.5 Size of sample item in rank Name of related sample. Ascending order A for sample 1 and B for sample 2 32 1B 38 2A 39 3A 44 B 41 5B 44 6.5 B 44 6.5 B 46 8A 48 9A 52 10B 53 11.5 B 53 11.5 A 57 13A 60 14A 61 15B 67 16B 69 17A 70 18B 72 19.5 B 72 19.5 B 73 21.5 A 73 21.5 A 74 23 A 78 24 A. From the above we find that the sum of the ranks assigned to sample 1 items are R1 equals 2 plus 3 plus 8 plus 9 plus 11.5 plus 13 plus 14 plus 17 plus 21.5 plus 21.5 plus 23 plus 24 equals 167.5, and similarly we find that the sum of ranks assigned to sample 2 items are R2 equals 1 plus 4 plus 5 plus 6.5 plus 6.5 plus 10 plus 11.5 plus 15 plus 16 plus 18 plus 19.5 plus 19.5 equals 132.5, and we have N1 equals 12 and N2 equals 12. Hence, test statistic UNNNR equals 12111112. Operator plus minus BG equals 12 12 12 12 12 1675 BG plus minus equals 144 plus 78 to 167.5 equals 54.5. Since in the given problem N1 and N2 both are greater than 8, so the sampling distribution of U approximates closely with normal curve. Keeping this in view, we work out the mean and standard deviation taking the null hypothesis that the two samples come from identical populations as under. 296 Research methodology Micro UNN equals 1 2 2 1 2 1 2 2 7 2 times equals BG sigma UNNNN equals plus equals plus 1 2 1 2 1 1 2 1 2 1 2 1 2 1 2 1 1 2 BG equals 17.32. As the alternative hypothesis is that the means of the two populations are not equal, a two-tailed test is appropriate. Accordingly, the limits of acceptance region, keeping in view 10% level of significance is given, can be worked out as under. Fig. 12.3 is the z-value for 0.45 of the area under the normal curve is 1.64. We have the following limits of acceptance region. Upper limit equals micro sigma UU plus equals 16472 1641732 10040. BG lower limit equals micro sigma UU minus equals 16472 1641732 4360. BG is the observed value of U is 54.5, which is in the acceptance region. We accept the null hypothesis and conclude that the two samples come from identical populations or that the two populations have the same mean at 10% level. We can as well calculate the U statistic as under using R2 value. UNNNR equals 122212. Operator plus minus BG equals 12 12 12 12 12 1325 BG plus minus equals 144 plus 78 to 132.5 equals 89.5. The value of U also lies in the acceptance region, and as such our conclusion remains the same, even if we adopt this alternative way of finding U. We can take one more example concerning U-test wherein N1 and N2 are both less than 8, and as such we see the use of table given in the appendix concerning values of Wilcoxon's distribution, unpaired distribution. 0.45 of area 0.45 of area 0.05 of area 0.05 of area limit 43.6 100.4 meters U equals 72 meters SUU plus 164 MSUU 164. Shaded portion indicates rejection regions. Testing of Hypotheses II 297 Illustration 6 2 samples with values 90, 94, 36 and 44 in one case and the other with values 53, 39, 6, 24, and 33 are given. Test applying Wilcoxon test whether the two samples come from populations with the same mean at 10% level against the alternative hypothesis that these samples come from populations with different means. Solution. Let us first assign ranks as stated earlier and we get Table 12.6 Size of sample item in ascending order. Rank name of related sample. Sample 1 is A. Sample 2 is B. 6 1 B 2 4 2 3 3 3 6 3 9 4 4 5 3 3 4 5 6 7 9 0 9 4 8 9. Sum of ranks assigned to items of sample 1 equals 4 plus 6 plus 8 plus 9 equals 27. No of items in this sample equals 4. Sum of ranks assigned to items of sample 2 equals 1 plus 2 plus 3 plus 5 plus 7 equals 18. No of items in this sample equals 5. BBABABAA. As the number of items in the two samples is less than 8, we cannot use the normal curve approximation technique as stated above and shall use the table giving values of Wilcoxon's distribution. To use this table, we denote W's as the smaller of the two sums and WL the larger. Also, let S be the number of items in the sample with smaller sum and let L be the number of items in the sample with the larger sum. Taking these notations, we have for our question the following values. W's equals 18, S equals 5, WL equals 27, L equals 4. The value of W's is 18 for sample 2 which has 5 items and as such S equals 5. We now find the difference between W's and the minimum value it might have taken, given the value of S. The minimum value that W's could have taken, given that S equals 5, is the sum of ranks 1 through 5 and this comes as equal to 1 plus 2 plus 3 plus 4 plus 5 equals 15. Thus, W's, minimum W's equals 18 to 15 equals 3. To determine the probability that a result as extreme as this or more so would occur, we find the cell of the table which is in the column headed by the number 3 and in the row for S equals 5 and L equals 4. The specified values of L are given in the second column of the table. The entry in this cell is 0.056 which is the required probability of getting a value as small as or smaller than 3 and now we should compare it with the significance level of 10%. Since the alternative hypothesis is that the two samples come from populations with different means, a two-tailed test is appropriate and accordingly 10% significance level will mean 5% in the left tail and 5% in the right tail. In other words, we should compare the calculated probability with the 298 research methodology probability of 0.05, given the null hypothesis and the significance level. If the calculated probability happens to be greater than 0.05, which actually is so in the given case is 0.056 greater than 0.05, then we should accept the null hypothesis. Hence, in the given problem, we must conclude that the two samples come from populations with the same mean. The same result we can get by using the value of WL. The only difference is that the value maximum WL is required. Since for this problem, the maximum value of WL given S equals 5 and L equals 4, is the sum of 6 through 9 i.e., 6 plus 7 plus 8 plus 9 equals 30, we have max WL equals 30 to 27 equals 3 which is the same value that we worked out earlier as W's, minimum W's. All other things then remain the same as we have stated above. B. The Kruskal-Wallis test, or H-test. This test is conducted in a way similar to the U-test described above. This test is used to test the null hypothesis that K independent random samples come from identical universes against the alternative hypothesis that the means of these universes are not equal. This test is analogous to the one-way analysis of variance, but unlike the latter it does not require the assumption that the samples come from approximately normal populations or the universes having the same standard deviation. In this test, like the U-test, the data are ranked jointly from low to high or high to low as if they constituted a single sample. The test statistic is H for this test, which is worked out as under 12 2 IHNNRNN1 IKN ARI summation equals plus minus plus BGBG3 1 equals 1 I where n equals n1 plus n2 plus nk and re being the sum of the ranks assigned to ni observations in the ith sample. If the null hypothesis is true that there is no difference between the sample means and each sample has at least 5 items, then the sampling distribution of H can be approximated with a chi-square distribution with k1 degrees of freedom. As such, we can reject the null hypothesis at a given level of significance if H value calculated, as stated above, exceeds the concerned table value of chi-square. Let us take an example to explain the operation of this test. Illustration 7. Use the Kruskal-Wallis test at 5% level of significance to test the null hypothesis that a professional bowler performs equally well with the 4 bowling balls. Given the following results, bowling results in 5 games with ball number A with ball no, B with ball no, C with ball no. D271 octodecillion 252 septendecillion 282 sexdecillion 275 quindecillion 257 quattordecillion 248 tridecillion 262 duodecillion 302 undecillion 260 decillion 279 nonillion 255 octillion 242 septillion 239 sextillion 297 quintillion 268 quadrillion 246 trillion 270 billion 276 million 266,258. If any of the given samples has less than 5 items, then chi-square distribution approximation cannot be used and the exact tests may be based on table meant for it given in the book, Non-Parametric Statistics for the Behavioral Sciences, by S. Siegel. Testing of Hypotheses II 299 solution. To apply the H-test or the Kruskal-Wallis test to this problem, we begin by ranking all the given figures from the highest to the lowest, indicating besides each the name of the ball as under. Table 12.7 Bowling results rank name of the ball associated 302 1B 297 2D 282 3A 279 4D 276 5B 275 6B 271 7A 278 D 268 9B 266 10C 262 11A 260 12C 258 13D 257 14A 255 15C 252 16B 248 17A 246 18C 242 19D 239 20C. For finding the values of Re, we arrange the above table as under. Table 12.7a Bowling results with different balls and corresponding rank ball A, rank ball B, rank ball C, rank ball D, rank 271 7252 16260 12279 4282 3275 6255 15242 19257 14302 1239 20297 248 17268 9246 18270 8262 11276 26610 15813 N1 equals 5R1 equals 52N2 equals 5R2 equals 37N3 equals 5R3 equals 75N4 equals 5R4 equals 46. Now we calculate H statistic as under. 300 Research methodology HNNRNNIIIK equals plus N Airy summation 1 2 1 3 1 2 1 BGBG equals plus RST UVW minus plus 1 2 2020 1525 375 755 465 320 12222 BGBG equals 0.02857 2362.8 63 equals 67.51 63 equals 4.51 as the 4 samples have 5 items each. The sampling distribution of H approximates closely with chi-2 distribution. Now taking the null hypothesis that the bowler performs equally well with the 4 balls, we have the value of chi-2 equals 7.815 for K1, or 4 to 1 equals 3 degrees of freedom at 5% level of significance. Since the calculated value of H is only 4.51 and does not exceed the chi-2 value of 7.815, so we accept the null hypothesis and conclude that bowler performs equally well with the 4 bowling balls. 6. One sample runs test. One sample runs test is a test used to judge the randomness of a sample on the basis of the order in which the observations are taken. There are many applications in which it is difficult to decide whether the sample used is a random one or not. This is particularly true when we have little or no control over the selection of the data. For instance, if we want to predict a retail store's sales volume for a given month, we have no choice but to use past sales data and perhaps prevailing conditions in general. None of this information constitutes a random sample in the strict sense. To allow us to test samples for the randomness of their order, statisticians have developed the theory of runs. A run is a succession of identical letters or other kinds of symbols which is followed and preceded by different letters or no letters at all. To illustrate, we take the following arrangement of healthy, H, and diseased, D, mango trees that were planted many years ago along a certain road. HHDDHHHHHDDDHHHDDDDHHHHHHHH 1 2 3 4 5 7 Street ND Road THTH 6 TH. Using underlines to combine the letters which constitute the runs, we find that first there is a run of 2 H's, then a run of 2 D's, then a run of 5 H's, then a run of 3 D's, then a run of 4 H's, then a run of 5 D's and finally a run of 9 H's. In this way there are 7 runs in all, or R equals 7. If there are too few runs, we might suspect a definite grouping or a trend. If there are too many runs, we might suspect some sort of repeated alternating patterns. In the given case there seems some grouping, i.e., the diseased trees seem to come in groups. Through one sample runs test, which is based on the idea that too few or too many runs show that the items were not chosen randomly, we can say whether the apparently seen grouping is significant or whether it can be attributed to chance. We shall use the following symbols for a test of runs. N1 equals number of occurrences of type 1, say H in the given case. N2 equals number of occurrences of type 2, say D in the given case. For the application of H test, it is not necessary that all samples should have equal number of items. Testing of hypotheses II 301 R equals number of runs. In the given case the values of N1, N2 and R would be as follows. N1 equals 20, N2 equals 10, R equals 7. The sampling distribution of R statistic, the number of runs, is to be used, and this distribution has its mean micro RNNNN equals ++2 1 1 2 1 2 and the standard deviation sigma RNNNNNNNNNN equals +++-2 2 1 1 2 1 2 1 2 1 2 2 1 2 BG. In the given case, we work out the values of micro R and sigma R as follows. Micro R equals ++ equals 220 10 20 10 11433 BG, and sigma R equals times minus plus minus equals 220 10 220 10 20 10 20 10 20 10 12382 BG. For testing the null hypothesis concerning the randomness of the planted trees, we should have been given the level of significance. Suppose it is 1% or 0.01. Since too many or too few runs would indicate that the process by which the trees were planted was not random, a two-tailed test is appropriate, which can be indicated as follows on the assumption that the sampling distribution of R can be closely approximated by the normal distribution. Fig. 12.4*. This assumption can be applied when N1 and N2 are sufficiently large, i.e., they should not be less than 10. But in case N1 or N2 is so small that the normal curve approximation assumption cannot be used, then exact tests may be based on special tables which can be seen in the book Non-Parametric Statistics for the Behavioral Science by S. Siegel. 0.495 of area 0.495 of area 0.005 of area 0.005 of area limit 8.19 20.47 MR equals 1433. MSRR plus 258. MSRR 258. Shaded area shows the rejection regions. 302 Research methodology. By using the table of area under normal curve, we find the appropriate z-value for 0.495 of the area under the curve, and it is 2.58. Using this we now calculate the limits of the acceptance region. Upper limit equals micro R plus 2.58 2.38 equals 14.33 plus 6.14 equals 20.47 and lower limit equals micro R 2.58 2.38 equals 14.33 6.14 equals 8.19. We now find that the observed number of runs, i.e., R equals 7, lies outside the acceptance region, i.e., in the rejection region. Therefore, we cannot accept the null hypothesis of randomness at the given level of significance, viz. Alpha equals 0.01. As such, we conclude that there is a strong indication that the diseased trees come in non-random grouping. One sample runs test, as explained above, is not limited only to test the randomness of series of attributes. Even a sample consisting of numerical values can be treated similarly by using the letters say, A, and B, to denote respectively the values falling above and below the median of the sample. Numbers equal to the median are omitted. The resulting series of A's and B's representing the data in their original order can be tested for randomness on the basis of the total number of runs above and below the median, as per the procedure explained above. The method of runs above and below the median is helpful in testing for trends or cyclical patterns concerning economic data. In case of an upward trend, there will be first mostly B's and later mostly A's, but in case of a downward trend, there will be first mostly A's and later mostly B's. In case of a cyclical pattern, there will be a systematic alternating of A's and B's and probably many runs. 7. Spearman's rank correlation. When the data are not available to use in numerical form for doing correlation analysis, but when the information is sufficient to rank the data as first, second, third, and so forth, we quite often use the rank correlation method and work out the coefficient of rank correlation. In fact, the rank correlation coefficient is a measure of correlation that exists between the two sets of ranks. In other words, it is a measure of association that is based on the ranks of the observations and not on the numerical values of the data. It was developed by famous statistician Charles Spearman in the early 1900s, and as such it is also known as Spearman's rank correlation coefficient. For calculating rank correlation coefficient, first of all the actual observations be replaced by their ranks, giving rank 1 to the highest value, rank 2 to the next highest value, and following this very order ranks are assigned for all values. If 2 or more values happen to be equal, then the average of the ranks which should have been assigned to such values had they been all different, is taken, and the same rank equal to the said average is given to concerning values. The second step is to record the difference between ranks, or D, for each pair of observations, then square these differences to obtain a total of such differences, which can symbolically be stated as n array summation D2. Finally, Spearman's rank correlation coefficient, R*, is worked out as under R Spearman's equals 1 Rs 6 TNNU 2 n array summation di minus 1 2 v ejw. Some authors use the symbol ρ for this coefficient. Rho is to be used when the sample size does not exceed 30. Testing of Hypotheses II 303, where n equals number of paired observations. The value of Spearman's rank correlation coefficient will always vary between plus or minus 1, plus 1, indicating a perfect positive correlation, and minus 1 indicating perfect negative correlation between two variables. All other values of correlation coefficient will show different degrees of correlation. Suppose we get R equals 0.756, which suggests a substantial positive relationship between the concerning two variables. But how we should test this value of 0.756? The testing device depends upon the value of n. For small values of n, i.e., n less than 30, the distribution of R is not normal, and as such we use the table showing the values for Spearman's rank correlation, table number 5 given in appendix at the end of the book, to determine the acceptance and rejection regions. Suppose we get R equals 0.756 for a problem where n equals 15 and want to test at 5% level of significance the null hypothesis that there is zero correlation in the concerning rank data. In this case our problem is reduced to test the null hypothesis that there is no correlation, i.e., R equals 0 against the alternative hypothesis that there is a correlation, i.e., micro r does not equal 0 at 5% level. In this case a two-tailed test is appropriate, and we look in the said table in row for n equals 15 and the column for a significance level of 0.05 and find that the critical values for R are plus or minus 0.5179, i.e., the upper limit of the acceptance region is 0.5179 and the lower limit of the acceptance region is minus 0.5179. And since our calculated R equals 0.756 is outside the limits of the acceptance region, we reject the null hypothesis and accept the alternative hypothesis that there is a correlation in the rank data. In case the sample consists of more than 30 items, then the sampling distribution of R is approximately normal with a mean of 0, and a standard deviation of standard error of R is sigma Rn equals minus 1111 n minus, and thus, we can use the table of area under normal curve to find the appropriate z values for testing hypotheses about the population rank correlation and draw inference as usual. We can illustrate it by an example. Illustration 8. Personnel manager of a certain company wants to hire 30 additional programmers for his corporation. In the past, hiring decisions had been made on the basis of interview and also on the basis of an aptitude test. The agency doing aptitude test had charged 100 rupees for each test, but now wants 200 rupees for a test. Performance on the test has been a good predictor of a programmer's ability, and 100 rupees for a test was a reasonable price. But now the personnel manager is not sure that the test results are worth Rs. 200. However, he has kept over the past few years records of the scores assigned to applicants for programming positions on the basis of interviews taken by him. If he becomes confident using 0.01 level of significance that the rank correlation between his interview scores and the applicants' scores on aptitude test is positive, then he will feel justified in discontinuing the aptitude test in view of the increased cost of the test. What decision should he take on the basis of the following sample data concerning 35 applicants? 304 Research methodology. Sample data concerning 35 applicants. Serial number. Interview score. Aptitude test score 181128883155938871386931476991160831285961160831285961390861285961390861466108129312815961312610815. Solution. To solve this problem, we should first work out the value of Spearman's R as under. Testing of Hypotheses II 305 Table 12.8, Calculation of Spearman's S. No. Interview aptitude rank differences squared score x test score xy difference. D2y rank x rank y 181113211563625635576353239981578924831299815789924.521 251063397659933225793887136136799582 1.530-28.5812 251076912626001160833428.55.530 2512859615.522 5749131266104161083118.512.5156 2515909595.524 to 14.5210 251669652936161787961322.5-9.590 2521811121165258211712522831928525-9.590 2522907999.531 to 21.5462 25236373330024781082 56367336827347121212127171128951211289512 to 10.5110 252981140214152713135851351315.5213.518 2533911181463634941473 512 56 2535941383.55 to 1.5225 n equals 35 n area summation equals D23583. 306 Research Methodology Spearman's equals 1 RDNNI 6116335351222 n area summation minus RST UVW equals minus times minus RST UVW EJ equals minus equals 121498428400498. Since n equals 35, the sampling distribution of R is approximately normal with a mean of 0 and a standard deviation of 1 n minus. Hence the standard error of R is sigma Rn equals minus 1.11351011715. As the personnel manager wishes to test his hypothesis at 0.01 level of significance, the problem can be stated: null hypothesis that there is no correlation between interview score and aptitude test score, i.e., micro R equals 0. Alternative hypothesis that there is positive correlation between interview score and aptitude test score, i.e., micro R greater than 0. As such, one-tailed test is appropriate, which can be indicated as under in the given case. Fig. 12.5. By using the table of area under normal curve, we find the appropriate z-value for 0.49 of the area under normal curve, and it is 2.32. Using this, we now work out the limit on the upper side as alternative hypothesis is of greater than type of the acceptance region as under. micro r plus 2.32, 0.1715, equals 0 plus 0.3978 equals 0.3978, 0.49 of area, 0.01 of area, limit 0.3978 meters, r equals 0 meters, SRR plus 232. Shaded area shows rejection region. Testing of hypotheses 2 307. We now find the observed r equals 0.498, and as such it comes in the rejection region, and, therefore, we reject the null hypothesis at 1% level and accept the alternative hypothesis. Hence we conclude that correlation between interview score and aptitude test score is positive. Accordingly, personnel manager should decide that the aptitude test be discontinued. 8. Kendall's coefficient of concordance. Kendall's coefficient of concordance, represented by the symbol W, is an important non-parametric measure of relationship. It is used for determining the degree of association among several k sets of ranking of n objects or individuals. When there are only two sets of rankings of n objects, we generally work out Spearman's coefficient of correlation, but Kendall's coefficient of concordance W is considered an appropriate measure of studying the degree of association among three or more sets of rankings. This descriptive measure of the agreement has special applications in providing a standard method of ordering objects according to consensus when we do not have an objective order of the objects. The basis of Kendall's coefficient of concordance is to imagine how the given data would look if there were no agreement among the several sets of rankings, and then to imagine how it would look if there were perfect agreement among the several sets. For instance, in case of, say, 4 interviewers interviewing, say, 6 job applicants and assigning rank order on suitability for employment, if there is observed perfect agreement amongst the interviewers, then one applicant would be assigned rank 1 by all the 4 and sum of his ranks would be 1 plus 1 plus 1 plus 1 equals 4. Another applicant would be assigned a rank 2 by all 4 and the sum of his ranks will be 2 plus 2 plus 2 plus 2 equals 8. The sum of ranks for the 6 applicants would be 4, 8, 12, 16, 20 and 24, not necessarily in this very order. In general, when perfect agreement exists among ranks assigned by k judges to n objects, the rank sums are k, 2k, 3k, nk. The total sum of n ranks for k judges is kn n plus 1, 2 and the mean rank sum is k n plus 1, 2. The degree of agreement between judges reflects itself in the variation in the rank sums. When all judges agree, this sum is a maximum. Disagreement between judges reflects itself in a reduction in the variation of rank sums. For maximum disagreement, the rank sums will tend to be more or less equal. This provides the basis for the definition of a coefficient of concordance. When perfect agreement exists between judges, W equals to 1. When maximum disagreement exists, W equals to 0. It may be noted that W does not take negative values because of the fact that with more than 2 judges complete disagreement cannot take place. Thus, coefficient of concordance W is an index of divergence of the actual agreement shown in the data from the perfect agreement. The procedure for computing and interpreting Kendall's coefficient of concordance W is as follows. A. All the objects, n, should be ranked by all k judges in the usual fashion, and this information may be put in the form of a k by n matrix. B. For each object determine the sum of ranks Rj assigned by all the k judges. C. Determine Rj and then obtain the value of S as under. Di2 equals minus SRRJJ. D. Work out the value of W using the following formula. 308 Research methodology. WSKNN equals minus 1, 1, 2, 2, 3 EJ, where SRRJJ equals minus DI2, K equals no of sets of rankings, i.e., the number of judges, N equals number of objects ranked, 1, 1, 2, 2, 3 KNN minus EJ equals maximum possible sum of the squared deviations, i.e., the sum S which would occur with perfect agreement among K rankings. Case of tied ranks. Where tied ranks occur, the average method of assigning ranks be adopted, i.e., assign to each member the average rank which the tied observations occupy. If the ties are not numerous, we may compute W, as stated above without making any adjustment in the formula, but if the ties are numerous, a correction factor is calculated for each set of ranks. This correction fact is TTT equals N Airy summation minus 312 EJ, where T equals number of observations in a group tied for a given rank. For instance, if the ranks on X are 1, 2, 3.5, 5, 6, 3.5, 8, 10, 8, 8, we have two groups of ties, one of 2 ranks and one of 3 ranks. The correction factor for this set of ranks for X would be T equals minus plus minus equals 2, 2, 3, 3, 1, 2, 2, 5, 3, 3 EJ EJ. A correction factor T is calculated for each of the k-sets of ranks, and these are added together over the k-sets to obtain n array summation T. We then use the formula for finding the value of W as under WSKNNKT equals minus n array summation 1, 1, 2, 2, 3 ej. The application of the correction in this formula tends to increase the size of W, but the correction factor has a very limited effect unless the ties are quite numerous. The method for judging whether the calculated value of W is significantly different from 0 depends on the size of n as stated below. If n is 7 or smaller, table number 9 given in appendix at the end of the book gives critical values of S associated with W's significance at 5% and 1% levels. If an observed S is equal to or greater than that shown in the table for a particular level of significance, then H0T, i.e., k-sets of rankings are independent, may be rejected at that level of significance. Testing of hypotheses 2309e. If n is larger than 7, we may use chi2 value to be worked out as chi2 equals k n1. W with d, f equals n1 for judging W's significance at a given level in the usual way of using chi2 values. F significant value of W may be interpreted and understood as if the judges are applying essentially the same standard in ranking the n objects under consideration, but this should never mean that the orderings observed are correct for the simple reason that all judges can agree in ordering objects because they all might employ wrong criterion. Kendall, therefore, suggests that the best estimate of the true rankings of n objects is provided, when W is significant, by the order of the various sums of ranks, Rj. If one accepts the criterion which the various judges have agreed upon, then the best estimate of the true ranking is provided by the order of the sums of ranks. The best estimate is related to the lowest value observed amongst Rj. This can be illustrated with the help of an example. Illustration 9. 7 individuals have been assigned ranks by 4 judges at a certain music competition as shown in the following matrix. Individuals A B C D E F G Judge 1 1 3 2 5 7 4 6 Judge 2 2 4 1 3 7 5 6 Judge 3 3 4 1 2 7 6 5 Judge 4 1 2 5 4 6 3 7. Is there significant agreement in ranking assigned by different judges? Test at 5% level. Also point out the best estimate of the true rankings. Solution. As there are 4 sets of rankings, we can work out the coefficient of concordance W for judging significant agreement in ranking by different judges. For this purpose we first develop the given matrix as under table 12.9 k equals 4 individuals, therefore n equals 7 A B C D E F G Judge 1 1 3 2 5 7 4 6 Judge 2 2 4 1 3 7 5 6 Judge 3 3 4 1 2 7 6 5 Judge 4 1 2 5 4 6 3 7. Sum of ranks Rj 7 1 3 9 1 4 2 7 1 8 2 4. N array summation equals Rj 1 1 2 R Rj j minus Di 2 8 1 9 4 9 4 1 2 1 4 6 4. Therefore S equals 332. 310 Research Methodology QRRNJJ equals 112716 QS equals 332. Therefore WSKNN equals 1 1 2 3 3 2 1 1 2 4 7 7 3 3 2 1 6 1 2 3 3 6 3 3 2 4 4 8 0 7 4 1 2 3 2 3 EJBG. To judge the significance of this W, we look into the table number 9 given in appendix for finding the value of S at 5% level for k equals 4 and n equals 7. This value is 217.0, and thus for accepting the null hypothesis H0 that k sets of rankings are independent, our calculated value of S should be less than 217. But the worked out value of S is 332, which is higher than the table value, which fact shows that W equals 0.741 is significant. Hence, we reject the null hypothesis and infer that the judges are applying essentially the same standard in ranking the n objects, i.e., there is significant agreement in ranking by different judges at 5% level in the given case. The lowest value observed amongst Rj is 7 and is such the best estimate of true rankings is in the case of individual A, i.e., all judges on the whole place the individual A as first in the said music competition. Illustration 10 given is the following information. K equals 13, n equals 20, W equals 0.577. Determine the significance of W at 5% level. Solution. As n is larger than 7, we shall work out the value of chi2 for determining W's significance as under chi2 equals k n1 W with n1 degree of freedom. Therefore chi2 equals 13 20 to 1 0.577, or chi2 equals 247 0.577 equals 142.52. Table value of chi2 at 5% level for n1 equals 20 to 1 equals 19 d. F is 30.144, but the calculated value of chi2 is 142.52, and this is considerably higher than the table value. This does not support the null hypothesis of independence, and as such we can infer that W is significant at 5% level. Relationship between Spearman's R, S and Kendall's W is stated above. W is an appropriate measure of studying the degree of association among 3 or more sets of ranks, but we can as well determine the degree of association among k sets of rankings by averaging the Spearman's correlation coefficients R's between all possible pairs, i.e., KC2 or KK12 of rankings, keeping in view that W bears a linear relation to the average R's taken over. Testing of hypotheses 2, 3, 11 all possible pairs. The relationship between the average of Spearman's R's and Kendall's W can be put in the following form. Average of R's equals KW1 K1, but the method of finding W using average of Spearman's R's between all possible pairs is quite tedious, particularly when K happens to be a big figure, and as such this method is rarely used in practice for finding W. Illustration 11. Using data of illustration number 9 above, find W using average of Spearman's R's. Solution. As k equals 4 in the given question, the possible pairs are equal to k1 2 equals 4, 4 to 1 2 equals 6, and we work out Spearman's R for each of these pairs as shown in table 12.10. Now we can find W using the following relationship formula between R's average and W. Average of R's equals KW1 K1, or 0.655 equals 4W1 4 to 1, or 0.6553 equals 4W1, or W equals plus equals 0.6553 1429654 0.741. BGBG. Note: this value of W is exactly the same as we had worked out using the formula. W equals S1/12 K2 N3N. Characteristics of distribution-free OR nonparametric tests. From what has been stated above in respect of important nonparametric tests, we can say that these tests share in main the following characteristics. 1. They do not suppose any particular distribution in the consequential assumptions. 2. They are rather quick and easy to use, i.e., they do not require laborious computations, since in many cases the observations are replaced by their rank order, and in many others we simply use signs. 3. They are often not as efficient or sharp as tests of significance are the parametric tests. An interval estimate with 95% confidence may be twice as large with the use of nonparametric tests as with regular standard methods. The reason being that these tests do not use all the available information but rather use groupings or rankings, and the price we pay is a loss in efficiency. In fact, when we use nonparametric tests, we make a trade-off. We lose sharpness in estimating intervals, but we gain the ability to use less information and to calculate faster. 4. When our measurements are not as accurate as is necessary for standard tests of significance, then nonparametric methods come to our rescue, which can be used fairly satisfactorily. 5. Parametric tests cannot apply to ordinal or nominal scale data, but nonparametric tests do not suffer from any such limitation. 6. The parametric tests of difference like T or F make assumption about the homogeneity of the variances, whereas this is not necessary for nonparametric tests of difference. 312 Research Methodology Table 12.10. Difference between ranks D assigned by k equals 4 judges and the square values of such differences D2 for all possible pairs of judges. Individuals: pair 1 to 2, pair 1 to 3, pair 1 to 4, pair 2 to 3, pair 2 to 4, pair 3 to 4. D2 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 A1 1 2 4 0 0 1 1 1 1 2 4 B1 1 1 1 1 1 0 0 2 4 2 4 C1 1 1 1 3 9 0 0 4 1 6 4 1 6 D2 4 3 9 1 1 1 1 1 1 2 4 EO 0 0 0 1 1 0 0 1 1 1 1 F 1 1 2 4 1 1 1 1 2 4 3 9 G 0 0 1 1 1 1 1 1 1 1 2 4 N area summation equals D2 8 N area summation equals D2 20 N area summation equals D2 14 N area summation equals D2 4 N area summation equals D2 28 N area summation equals D2 42 Spearman's coefficient of correlation RDNN equals minus N area summation minus 16122 EJR 12 equals 0.857 R13 equals 0.643 R14 equals 0.750 R23 equals 0.929 R24 equals 0.500 R34 equals 0.250. Average of Spearman's S equals 0.857 plus 0.643 plus 0.750 plus 0.929 plus 0.500 plus R0250 6 equals 3929 60655. Testing of Hypotheses II 313 Conclusion. There are many situations in which the various assumptions required for standard tests of significance, such as that population is normal, samples are independent, standard deviation is known, etc., cannot be met, then we can use non-parametric methods. Moreover, they are easier to explain and easier to understand. This is the reason why such tests have become popular. But one should not forget the fact that they are usually less efficient, powerful, as they are based on no assumption, or virtually no assumption, and we all know that the less one assumes, the less one can infer from a set of data. But then the other side must also